Hello, in this video I wanted to show how you can get momentum out of the wave function. So we've talked about expectation values before, and how if you want to find the average value for a particle x, you want to find the average position of it's really a wave, but what is its average position? And we said that what that means is you take the wave function and you integrate x times the complex conjugate of the wave function, and then times the wave function itself. If you integrate this over the all of space, you get the expectation value of x. And you can put x in there, you can put x squared in there. We've done a few things that way. What I wanted to talk about now is what if you want to find out the momentum? What if you want the average momentum of this wave? The wave has some momentum. I mean, we think of it classically as a particle, and it certainly has momentum. So how do we do this? What do we need to put in here? What is, I could just write a p there, but what is it? What is the momentum that I'm actually integrating over? What does it depend? How does it depend on the wave function? Is it, it's not, how does it depend on position? So to figure this out, we can look at our example of a particular solution of the wave function where we said, when we had just no potential at all, we said that it looks like just a freely propagating wave, and we had something that looks like, if we actually include the time part, we had something that looks like this. There's some normalization, which I'm not going to worry about. We said we get a wave, and one way we can write a wave in space and time is like this. And so this is actually a nice example to work with when we're thinking about momentum, because this is a wave, it's spread out everywhere in space. If we tried to calculate its average position, this integral would never converge, because this thing oscillates forever. It has no position really at all. On the other hand, what that does mean is, if we think about the uncertainty principle, that means it has a very specific momentum. Because it has a very specific wavelength. This is a wave that goes on forever, so its wavelength is very precisely defined. And if you remember that the relation between momentum and wavelength is just this de Broglie relation, that wavelength was h over p, and then we said, you know what, we can define 2 pi over lambda as the wave number, and so we have, we ultimately get to that. Another way of writing this is p is h bar times k. And that's the same k that comes up here. So that k really is, in different units, it's really a measure of the momentum. And so then the question is, okay, so how do we get the momentum out of this function by just using things that act on x? And we've already actually seen this. We've actually already seen the answer in the Schrodinger equation. That gave us a hint. Because what happens if we take a derivative of this function? We get a factor of k down, as well as some other stuff. But let's write that out. So d psi dx equals, I'm going to bring down a factor of I and k, and then I'll get back the original wave function. So d psi dx is just I times k times the wave function. And so if I say, well, k is just p over h bar, then I can write this I p over h bar psi. And then let me rearrange things a little bit. Let me write this as p times the wave function equals, and then I'm going to write h bar over I. But actually, I can rewrite h bar, well, I'll write that right now. H bar over I times partial by partial x of the wave function. So that, in fact, is how what we're going to plug in here, where I put this question mark, for how we find momentum. So we call this an operator, because it's not just a number that you multiply by the wave function. You actually have to take a derivative here. But you take this and you stick it in here, and so you just have an h bar over I d by dx. And that's why I wrote this. You might not have seen me write things in the middle before, but now we have to be a little bit careful about where we put things, order matters here, but the way we want to do this is we want to take the derivative of just one of the wave functions. So it makes it's clearest if we put it in here sort of in the middle. So when we want to find the expectation value of the momentum, we just take the complex conjugate of the wave function and then put it in h bar over I d by dx, and not really multiplied by the wave function, but acting on the wave function. And then we integrate that. And so that's how we find the momentum. And just as an aside, I think in your book it writes it slightly differently, but you can change this h bar over I. If you multiply top and bottom by I, then I times I is just -1. And so this is just this is also equal to minus I h bar d by dx of psi. So a lot of so the way this is often written is we just sort of drop the size, the wave function itself here, and we write this as, sort of ran out of room here, but I'll write it over to the right here. We write this as sort of P, the momentum acting as an operator, equals minus IH bar partial x. And so whenever we're doing an expectation value, that's what we put in. And so if we're finding the expectation value of momentum, we put that in. If we're finding the expectation value of momentum squared, we just do this twice, and so we'll have a second derivative. You get the minus IH bar, those are constants you can pull out but of the derivative, but when you act with a derivative on another derivative, you're taking a second derivative, so keep that in mind. But that is how we treat momentum in quantum mechanics. And later on, we're going to see actually we treat a lot of things as operators. In general, most operators aren't just simple multiplication like x, like position was, but we can think of energy as an operator, kinetic energy as an operator, angular momentum we can think of as an operator, so we'll get to that later on. But basically, any of these possibilities, we can figure out how they work by treating them as operators and acting them on the wave function. All right, thanks for watching.